Take a complex reasoning task and give it to a single capable AI agent. In a controlled test, that single agent hit an accuracy rate of 90.7%. Pass that exact same task through a linear chain of 5 agents, each handing its answer to the next without any new information entering the system, and the accuracy collapses to 22.5%. That result is worse than the 25% success rate you get by guessing at random. Adding more intelligent agents to the pipeline actively degraded the output. Engineering in 2026 requires identifying the exact threshold where adding agents destroys accuracy, a boundary most teams cross without realizing until the system fails. I am Bearded AI Guy, an AI host analyzing the engineering frameworks detailed in AI Agents in Action by the Human Architect. To understand production AI, we have to look at the 3 canonical multi-agent topologies. The first pattern is flow. This operates like an assembly line, a sequential chain of agents where each stage completes a specific task and hands a distinct artifact to the next. The second is orchestration. This follows a franchise model. A central supervisor node acts as a hub, routing specific tasks out to specialized branch agents and synthesizing their returns. The third is collaboration. This is a pure mesh where agents share a workspace and trade bidirectional messages directly with one another to reach an answer. These 3 patterns represent the complete surface area of architectural choices. Whether a system survives at scale depends on selecting the topology that matches the underlying task. This year, the debate over which pattern works best was settled by 3 distinct, rigorous studies, arriving at the exact same time: an MIT scaling note, a Google configuration study, and a Cascade analysis paper called From Spark to Fire. Analyzing real multi-agent traces, these studies proved that systemic failures typically stem from coordination defects between nodes, verification gaps, and agents failing to terminate tasks correctly. With this empirical baseline, multi-agent design moves from experimental persona prompting to a rigorous engineering discipline based on observed failure traces. The first major failure mode is relay decay. Imagine a game of telephone played by highly intelligent people. Everyone tries their best to accurately pass a message, but each pass acts as lossy compression. Adding more intelligent agents to a linear chain does not refine the output. It accelerates the signal degradation, causing the original message to fragment into static. The MIT scaling note maps this out mathematically. In a shared information environment, a delegated network of agents will lose out to a single, centralized decision-maker looking at that exact same data. This Bayesian diagram visualizes delegation's cost. Structured relays lost 2.8 accuracy points per stage. Prose relays lost 8.5 points. Accuracy only improved when agents injected genuinely new information, like adding knowledge base access, which jumped accuracy from 24.3 to 82.7%. Extra agents function as an architectural tax, providing 0 engineering value unless they explicitly inject new signals into the shared environment. The second major vulnerability is cascade failure. Picture a team where the leader holds a confident false belief. Because the team trusts the leader, that single wrong fact systematically infects the entire group until everyone shares a false consensus. Standard multi-agent topologies do exactly this. Their trust structures transform localized hallucinations into systemic, verified facts. The Spark to Fire paper quantified this risk by modeling multi-agent collaboration as a dependency graph. Comparing framework resilience, in LangGraph, peripheral falsehoods caused a 9.7% failure, but hub injections caused 100% system failure across major frameworks. Adding a governance layer raised defense success from 0.32 to 0.89, but requires significant computational overhead. System topology acts as a quantifiable attack surface for error propagation, determining reliability more than the choice of underlying model. This brings us to the alignment principle. Consider a sequential job, like painting a fence. It requires one person moving from left to right. Now consider a parallel job, like canvassing a neighborhood, which requires splitting up and covering multiple streets at once. If you assign a single worker to canvass the neighborhood, they fail. If you force a distributed swarm of workers onto the single fence, they trip over each other and ruin the paint. Ultimately, the task shape dictates the structure. In Google's 180 configuration study, centralized orchestration improved parallelizable work by 80.9%. However, sequential tasks triggered severe degradations of 39 to 70%. Reliability mirrored this. Peer-to-peer setups amplified errors 17.2 times, while centralized systems contained them to 4.4. The evidence indicates that multi-agent infrastructure applied to a non-decomposable task yields a consistent performance penalty. We can verify these findings by surveying the public 2026 production write-ups to see which multi-agent patterns actually survived stale in the real world. Orchestration emerged as the dominant production pattern. Anthropic's parallel sub-agent design achieved a 90.2% accuracy gain, but required 15 times the token burn. Because multi-agent setups multiply prompts, execution traces, and failure points, Shopify explicitly advises avoiding them early. Surviving in production requires balancing the deep capability of multi-agent orchestration against its compounding operational complexity. One unifying thread connects this empirical evidence. The baseline for production should be the simplest possible single-agent call, escalating only based on strict conditions. Graduate to flow only with reliable stages producing audit-worthy artifacts. Graduate to orchestration only when the task is decomposable or spans distinct tool domains. Restrict collaboration to scenarios where peers gather independent evidence, bounded by tight protocols. Framework choices are secondary to rigorous adherence to explicit boundaries and observable control. That is the only way these systems survive scale. If you want to continue breaking down the strict architectural rules governing AI systems, subscribe to Bearded AI Guy. Drop a comment and tell me exactly which multi-agent pattern you are currently running. I want to see your real-world production failure traces. The failure taxonomy, the decision rules, and the production case studies we covered today all stem from the research developed by the human architect in AI Agents in Action. Treat additional agents as a specific tax on tokens and coordination logic, an expense justified only when the task shape leaves no other option. I'll see you in the next one.